everyone. Well, my presentation will deal with some models of beam columns and some issues of instabilities connected also to the type of instabilities, divergence or flutter. Well, we know that for conservative systems, instability can occur only by the divergence. And the presence of discontinuities generally produce both a reduction of the buckling load and a modification of the buckling shapes. But in the aeronautical engineering, sometimes structures are subjected to non-conservative forces. And in this case, the damage can produce also a modification in the type of instability, which can be of flutter type. In a previous paper, we studied the effect of concentrated damage on the dynamic instability of a cantilever beam column subjected to conservative and non-conservative forces. And we discovered that the presence of damage distribution not only can alter the value of the critical load, but also can provide a strong modification of the type of instability. Then we also demonstrated that the position and the damage intensities play an important role in the values of the critical loads and in the boundaries which identify the transition between divergence and flutter. Well, on the other hand, the tensile instability phenomenon has rarely been studied in the literature. And to the author's knowledge, no one studied tensile instabilities in the non-conservative force context. So the question which has arisen from our thoughts is if a beam column can undergo tensile flutter. To answer these questions, we have to study, to show something in the literature about the tensile buckling studies. There are very few papers on this topic, and these studies are limited to Timoshenko beam columns or columns with high deformability due to, like for example, multi-layer elastomeric bearings, or in weakened Timoshenko columns. On the other hand, there are a few studies on Euler-Bernoulli beam columns in presence of structural junctions and with a constraint with a curved constraint. I would like to show that all these studies which treat different models can be somehow viewed under the same perspective. And in particular, I would like to interpret the tensile buckling phenomenon like a phenomenon which can occur in presence of shear deformability only, either distributed or concentrated. That's why I will deal with two different contexts, conservative force and non-conservative forces. And for the conservative force, I will consider two different models, the uniform Timoshenko beam columns and the Euler-Bernoulli beam columns in presence of multiple internal elastic sliders. And I will show that somehow these two models can be related one to each other. And then I will move to the non-conservative context. Well, the first model we have considered is the Timoshenko uniform beam column. And this is the equation of motion in the dimensionless form, in which we introduce the load parameter, the frequency parameter, the shear stiffness parameters in terms of mechanical properties and geometric properties, and an additional load parameter. The equation of motion can be rewritten in this form, in which we introduce what we call the Timoshenko load parameter and the Timoshenko frequency parameter, even if these names are somehow improper, because both of them are coupled in the classic frequency and load parameters. The solution of this equation is well known and can be provided as a function of 4 integration constants only, and as a function of these h functions. Well, the first thing we did is to explore both the compressive side and the tensile side for a clamped beam column. For the compressive side, we did this for different values of the shear stiffness. For the compressive side, we saw that as the load increases, the frequency decreases until it drops to 0 with the occurrence of divergence instability. If we increase the load in the tensile side, there is first an increasing in the frequency parameter, then a range in which the frequency decreases, and then there is a crossing between two frequency curves. And then the frequency quickly drops to 0. And this crossing of the two curves leads to the occurring of an antisymmetric instability shape. Then we moved to the Euler-Bernoulli beam column in presence of multiple internal elastic sliders which connect the shear force with the jump in the deflections. The mass is considered uniformly distributed and there is no damping. We treated the presence of multiple internal elastic sliders by means of a distributional theory. So the equation of motion has been modified in this way. We have somehow the same equation with the classic load frequency parameters, but on the second member we have considered the elastic sliders discontinuities by means of a distributional theory in terms of Dirac's delta function. And the summation means that we can consider as much sliders as we want. The parameter lambda represents the normalized translational spring compliance. The solution can be provided in this form, and as you may see, it is a function of 4 integration constants only, irrespectively of the number of internal discontinuities considered. And this is a great advantage because we have not to enforce the continuity condition at each discontinuity. These functions depend on the h functions, which formally coincide with those relative to the Timoshenko uniform beam column, and an additional function h with hat relative to the generic internal slider that we find in the solution in the summation 4. Okay, these results are relative to a clamped Euler-Bernoulli beam column with a single internal slider for 2 different positions of the slider and for an increasing compliance of the slider. The straight line represents the response of the uniform Euler-Bernoulli beam column, which provides a divergence in compression, but no instability in tension. But as we introduce a slider compliance, we have both divergence in compression, but also in tension. And in our opinion, introducing a slider is like considering a concentrated shear deformability. And we can also see that there is a crossing in the frequency curves. So when the curves share a range with the uniform Euler-Bernoulli beam column, it means that the mode shape is the global one and not the slider one. These are the results which reproduce an experimental test led in Italy by the research team of Professor Bigoni, in which the first four eigenfrequency curves are reported for an Euler-Bernoulli beam column with a structural junction. And these are the results in terms of first frequency parameter versus the elastic compliance for a given position of the elastic slider and for different values of the axial load. You may see that there is a range in which the frequency doesn't undergo modifications as the compliance increases. And these ranges correspond to those in which the mode is the global one and not the slider one. Well, I will skip some slides to go faster. And anyway, I want to highlight that this strategy allows to consider an arbitrary number of sliders with no difficulty. For example, in this case, we have the eigenfrequency curves for a number of 10 equally spaced elastic sliders for different values of the compliance. And on the right, we have, for a given value of the compliance, the eigenfrequency curves for an increasing number of equally spaced sliders. Well, the next step is to relate somehow the number and the compliance of the sliders of the Euler-Bernoulli beam column with the shear deformability of the uniform beam columns. And we consider this relation, with this simple relation, in which the shear stiffness is related to the number and the compliance of elastic sliders in the Euler-Bernoulli beam column. And we discovered that if we consider the first frequency for both in compression and in tension for different values of the axial load and for a given shear stiffness, we discovered that the more we increase the number of the internal sliders in the Euler-Bernoulli beam columns, the more the continuous line, which is relative to the beam columns, approaches the dashed line, which is relative to the Timoshenko column. And this can be found also in terms of eigenfrequency curves. For a given shear stiffness, we plotted the dashed line, which represents the Timoshenko uniform beam column, and several curves relative to the Euler-Bernoulli beam column with an increasing number of equally spaced internal sliders. Also, in terms of critical loads, we can see that the more we increase the number of internal sliders, the more the curve relative to the Euler-Bernoulli model approaches the Timoshenko uniform beam column. Well, this is a first part of remarks. That is, we treated the tensile buckling phenomenon for different models. And in particular, uniform Timoshenko and Euler-Bernoulli with shear discontinuities beam columns has been explored. I presented the closed form expressions of the eigenmodes of Euler-Bernoulli beam columns in presence of an arbitrary number of internal sliders. And a closed form of the characteristic equation can be provided. The model for the Euler-Bernoulli with discontinuities requires the enforcement of 4 boundary conditions only, irrespectively of the number of the internal elastic sliders. And we also presented a parametric study which deals with the number, the position, and the compliance of internal elastic sliders. Another important aspect is that tensile compressive instability in presence of single or multiple elastic sliders occurs at similar values of the axial load. And last, a comparison between the 2 structural models has been provided. In particular, the Euler-Bernoulli beam column seems, with multiple internal elastic sliders, seems to be the discrete counterpart of the continuous uniform Timoshenko beam column. Well, the last step was to consider the Euler-Bernoulli beam column in presence of shear discontinuities in the non-conservative context. So we considered a cantilever beam column subjected to an end force in which the degree of non-conservativeness is ruled by the parameter eta. In particular, when eta is equal to 0, it means that the force is fully conservative. Eta equal to 1 corresponds to the case of pure follower force. Well, in this first application, we can see the cantilever Euler-Bernoulli beam column with a single internal elastic sliders. When no slider is considered, we can find, for the case of pure follower force, flutter. That is when the two frequencies tend to coincide. We find fluttering compression and no instability in tension, either divergence or flutter. But as we increase the compliance of the slider, we find flutter also in tension. Okay, last 2 slides. In this one, we report the critical load both in compression and in tensile, in tension versus the position of the slider. And we discovered 2 strange things, or unexpected things. The first one is that in compression there is a range in the position of the slider in which the critical load is higher than the corresponding one relative to the uniform Euler-Bernoulli beam column. The second is that as the slider approaches to the free end, there is a clear crossing of curves, and this will be clear in a while. In this case, we reported the maps in which the transition between divergence and fluttering instability occurs. This transition is important because it is often it leads also to a sudden drop in the critical load. So these transition curves are reported in terms of degree of non-conservativeness versus the slider position. And the dashed line corresponded to the uniform Euler-Bernoulli beam column, and we have this transition only in compression but not in tension. The interesting aspect is that there is some areas in which the flutter occurs not between with the coincidence of the first and second frequencies, but between the second and the third one, as you may see in this picture. I finish it. I will skip the general case. In conclusion, we studied tensile flutter type instabilities for the first time in the literature. The occurrence of these instability is strictly dependent on the shear deformation, again with the internal elastic sliders. And it has been shown that the model leads to tensile flutter instability never encountered in the literature. And also the maps in terms of non-conservative parameters which identified the transition between divergence and flutter instability have been provided. Thank you, everyone.